I, Dr.S.Pethanachi Selvam, Associate Professor and Head, PG and Research Department of Mathematics, SFR College, Sivagasi. At this session, I am going to take Introduction of Matrix Theory. Here, what is the definition of a matrix, how it is framed as a mathematical definition, what are its applications, and what are the types of matrices, how the operations are applied on matrices, and properties of matrices. Here the learning outcomes are how to form the matrix definition and what are the application of matrices and types, operations and properties of matrices. Usually matrix is a rectangular or square array of numbers, symbols or expressions arranged in the form of rows and columns. The number of variables in the matrix are called entries or elements of the matrix. The size of the matrix or order of a matrix is determined by its rows and columns. In real life situation, if you take an example, a furniture company makes chairs and tables at its 3 factories. The total production in hundreds from the 3 factories for the 2 years 22 and 23 is listed below. Here 3 factories are given in Roman letter and the products are given as chairs and tables. We can represent those production of the company for the 2 years can be represented in matrix form. Matrices are usually denoted by capital letters. Here the rows, first row A matrix is 30 chairs in the first factory and 18 tables. That's why here the matrix first row having the values 30 and 18. And second factory produce chairs 20,000 and tables 12. So each one is 100. So 20, 100 and 1200. So the second row 20 and 12. The third factory produce chairs 1600s and tables 1000s. So it is given as the 16 and 10. The matrix is represented by capital letter A. Similarly, for the production in the year 2023 is represented in the matrix capital B. Now, what are the applications in real life situation? The applications of matrix plays a major role in mathematics as well as in other fields such as engineering, life sciences, economics, geology, cryptography, computer graphics, finance and so on. Matrices provide a useful tool for working with models based on systems of linear equations. Matrices are useful in organizing and manipulating large amount of data. In graphics, usually many applications, let us see one by one. A square matrix is a simple way to present linear object transformations. In graphics, matrices are used to project 3-dimensional images into 2-dimensional planes. A digital image can be treated as a matrix in graphics. The matrix rows and columns correspond to the rows and columns of pixels and the numerical entries correspond to color color values of the pixels. In video game graphics, manipulating and point with matrices is a typical mathematical strategy. Graphs are also represented using matrices. How we can represent a matrix mathematically? Here take an M cross N matrix. It is a rectangular array of M1 numbers. The numbers are arranged in M rows and N columns where I varies from 1 to M and J varies from 1 to N. We shall denote this matrix by the symbol small aij within the open bracket. That is, the matrix is denoted by capital letter A and that symbol as open bracket small aij. I represent number of rows and j represent number of columns. Here the rows of the matrix is m rows and columns will be n. For example, here the matrix A is given. Here this matrix is 3 rows and 4 columns. 3 rows are 0, 4, 3, 5. It's a first row. Second row as 1, -1, 6, 5. And third row 0, 0, 1, 2. Here let us see the next one. What are the types of matrices? If you have an 1 row and n column matrix is called as a row matrix. That is only 1 row. And an m cross 1 matrix, that is m rows and only 1 column, it is called as a column matrix. And n cross n matrix is called a square matrix. Let us take a square matrix A, then the elements A11, A22, etc., ANN are called the, that is A11, 22 and etc. NN are called the diagonal elements of A and are known as principal diagonal elements of the matrix A. A square matrix is said to be a diagonal matrix if all the entries which do not belong to the principal diagonal are 0. For example, in mathematically we can say that in a diagonal matrix all the entries I not equal to j, that is except the principal diagonal entry, all the entries to be 0. Mathematically it is denoted as aij equal to 0 for all I not equal to j. For example, you see that the diagonal principal diagonal entries are 1, 3, 2 and other entries of the 3 cross 3 matrix are 0. So this is an example of diagonal matrix. Here what are the subdivisions of this diagonal matrix? That is, a diagonal matrix is said to be a scalar matrix. When do you say that? That is, the principal entries should be a scalar number. Here for example, the principal diagonal entries are the scalar 4, 4, 4. It is a scalar matrix. Any scalar may be given in the principal diagonally. And another subdivision is a unit matrix. If you have a diagonal matrix in which all the diagonal entries are 1, 1, then we can say that it is a unit matrix or identity matrix. It is usually denoted by capital I. Here in example, a square matrix of order 2 is given 1, 0, 0, 1. It is a scalar matrix as well as it is a unit matrix. And next one, 2 subdivisions of the triangular matrices. Before defining triangular matrix, we can define what is meant by upper triangular matrix and next one lower triangular matrix. Then only we can say that the square matrix is a triangular matrix. Here first we can see the upper triangular matrix. A square matrix is said to be an upper triangular matrix if all the entries above the principal diagonal are 0. That is, mathematically aij equal to 0 if I less than 0. Then only the matrix is said to be an upper triangular matrix. Then lower triangular means it is all the entries below the principal diagonal are 0. You can see the example, aij equal to 0 if I greater than j. Then only it is a lower triangular matrix. Here the first example is all the entries below the diagonal, that is called as it is a example for lower and upper triangular matrices, and you can see the upper triangular and the lower diagonal examples are given. That is, below the diagonal all the entries are 0, it is called as a lower triangular, and upper triangular all the upper diagonal element, the elements above the principal diagonal are 0, it is named it as a upper triangular matrix. Therefore, we can combine the upper triangular and lower triangular matrices, we can define the triangular matrix. A square matrix is said to be a triangular matrix if it is both lower triangular as well as upper triangular matrix. Now the next definition, that is symmetric matrix. When do you say that a matrix is said to be symmetric? That means the rows and columns are interchanged. Usually in English we say like that. In symbolically we can write aij, that is all the entries of the matrix equal to aji for all I and j. Here the example is given. Here the example 1, 2, 3, it's a principal diagonal. You can watch the other elements a12 minus 5 and here it is changed into a21. a13 element is 7 and here it is given as a31, and similarly a23, that is the element 2, and here it is given as A 3 2, which is also 2. Therefore, this is an example of symmetric matrix. Then the next matrix is a skew symmetric matrix. That means here you have to change the sign. That means if Aij equal to minus Aji for all I and j. Here we can see the example. Here one more difference. Here all the principal diagonal entries should be equal to 0. These are the important property in skew symmetric. Because you see that the elements entries are changed. The element 1 2, A12 element is minus 2, whereas A21 entry is plus 2. That's why Aij equal to minus Aji. Here the properties, whenever you take a skew symmetric matrix, Aii equal to minus Aii, then what will happen? 2 times Aia equal to 0. That means Aii equal to 0 for all I. That's why all the principal diagonal entries of a skew symmetric matrix is 0. And you can say that in a skew symmetric matrix, all the diagonal elements are 0. And similarly, you can define Hermitian and skew Hermitian. Here in Hermitian matrix, the entries may be complex numbers. That is, a square matrix is said to be a Hermitian matrix if Aij equal to Aji the whole bar, where bar denote the conjugate of the entry. Here you can take the example. The first diagonal elements are 1 and 3. You can see the entry of 1 2. 1 2 entry is minus 1 plus 2i. It will become A2i, A21 the whole bar. Therefore, the conjugate is the conjugate of the entry as it is minus 1 plus 2i, and it is changed into another element Aij equal to Aji the whole bar. Therefore, 3 minus 4i. The value will be a Hermitian matrix. Its conjugate, the element is wrongly entered, and in a Hermitian matrix, Aia equal to Aia the whole bar. If Aia or should be a real number, always the diagonal entries are real entries. And the next one is, suppose any Hermitian matrix, all the entries are real, means it will become a symmetric matrix. And next one is a skew Hermitian matrix. Here in skew Hermitian matrix, you can see that, take an example, and here the elements are changed. Aij equal to Aij the whole bar. That means you change the entries. The diagonal entries are the same, IB and IB, whereas C plus ID is changed into minus Aij the whole bar. That's why the element is changed. Here the element is minus C plus ID, and similarly A plus IB is changed into minus A plus IB is changed into A plus IB. In a skew Hermitian matrix, some more properties are there. Suppose the diagonal entries, what will happen? Aij equal to minus Aii the whole bar means, that means the value will become Aia equal to 0. That means it is a purely imaginary part. Therefore, it is only 0 or otherwise purely imaginary. That's why the above examples, the two diagonal entries are purely imaginary. In the other example, it should be equal to 0. A skew Hermitian matrix over R is again, over R means it will become a skew symmetric matrix. And then the next type of matrix is very important matrix, that is orthogonal and unitary matrices. Here a real matrix is said to be a real square matrix. In the previous Hermitian and skew Hermitian matrices only for, it also included for complex numbers, but here a real square matrix is said to be orthogonal if A transpose equal to A transpose A equal to 1. Here you can transpose, we can interchange the rows and columns. Then you can get the value cos theta sin theta in the first row minus sin theta and cos theta. You take a transpose matrix, you multiply the two matrices, you can get it cos squared theta plus sin squared theta, the value will become 1, and another one sin theta cos theta minus cos theta sin theta, that's why the value will become 0. So you can get A transpose equal to the unitary matrix, that is named it as I. That's why A transpose equal to I. So the matrix A is orthogonal. Similarly, you can define unitary matrix. Here the entries may be real or the entries may be complex valued. A square matrix A is said to be unitary matrix if A transpose equal to or A transpose A equal to identity matrix. For example, you take this is an unitary matrix. You find the conjugate A bar transpose. It represents conjugate and then take conjugate and then take the transpose, and A bar the conjugate value is given 0i and minus I 0. Then only you interchange the rows and columns, you can get A bar transpose. Then you multiply it, again you can get the identity matrix I. The properties are given below. The unitary matrix over R is always an orthogonal matrix, and a square matrix is said to be an idempotent. You can say that if A squared equal to A, and a square matrix is said to be an that is a unitary matrix, that is it is said to be A bar, again the definition is repeated, we can omit it, and a unitary matrix, here again the properties, we can omit it. Then involutory, when do you say that? Here the what are the operations we have to add it. Here two matrices are said to be equal. We say that if they have same number of rows and same number of columns, as well as the corresponding entries in the two matrices should be the same. And if you have two matrices, both of order m cross n, then only the sum of two matrices is possible and the order of the matrix to be equal to m cross n. It is an example is given, and two matrices can be, how we can be multiply two matrices. The first matrix is of order m cross n and second matrix is of order n cross p, then AB is possible. That means number of columns of first matrix equals the number of rows of the second matrix. We can get the matrix to be Cij. The entries are denoted as sigma Aik Pkj. And here we can come to the next one, the example. The product of two matrices is determined only when the columns of A equal to the number of rows of B. And next one is the transpose. That is, if you have an m cross n matrix, then the transpose matrix is of order n cross m. In symbolically, the entries of the matrix B will be Pij equal to Aji, and it is denoted by A transpose T, the symbol A transpose. You can see the example. The matrix A equal to first row 1, 2, 3, 4, second row 0, minus 1, 5, 6. Interchange the rows, therefore the number of rows, columns will be the rows 1, 0, second column will become A transpose second row 2 minus 1, and third column 3, 5 will become third row, and the fourth column of A will become the fourth row, 4 and 6 will become 4 and 6 the fourth row. Therefore, here you can see A is of order 2 cross 4, whereas A transpose is of order 4 cross 2. And then the next one is properties. What are the properties of matrices? If A is an m cross n matrix, then A transpose will be of order n cross m. AB and both AB and BA cannot be defined for any matrices. When does it will be possible? That means if A is an m cross n matrix and B is an n cross m matrix, or both A and B are of same order, then only AB and BA can be defined. If A is any square matrix, then A squared can be determined. If A is symmetric, then A transpose is symmetric. If A is a skew symmetric matrix, then A squared is symmetric and A cube is skew symmetric. A and B are symmetric matrices of same order, then AB plus BA, AB minus BA is a skew symmetric matrix. A and B are orthogonal matrices of same order, then A transpose and AB are orthogonal matrices. A and B are unitary matrices of same order, then AB is also a unitary matrix. The sum of two symmetric, skew symmetric, Hermitian and skew Hermitian matrices of the same order is respectively symmetric, skew symmetric, Hermitian and skew Hermitian matrix. Any square matrix A can be uniquely expressed as a sum of Hermitian symmetric matrix as well as and a skew symmetric and skew Hermitian matrix. here two types of different types of matrices, AB equal to BA and BA equal to B means then the property says that both A and B are identity matrices. If A is an idempotent matrix, then I minus A is also an idempotent matrix. A square matrix is involutory if and only if I plus A into I minus A equal to 0 matrix. Thank you. Thank you to watch this video. Thank you all.